Hi everyone, so welcome to this video on backpropagation algorithm, and this algorithm has been considered as one of the most challenging difficult things in entire machine learning, right? So the reason is that it involves some knowledge of linear algebra and calculus, and given the formula it is not very difficult to implement, but the important thing is how that formula came. How do you derive your own backpropagation logic that we are going to learn in this videos, and later on we are going to implement backpropagation to make a classifier, and you can also build a cool Pokemon classifier like this one shown in the figure, and maybe you can later on use GANs to generate your own Pokemons as well, right? So it's deep learning is quite a fun, and in this video I will be talking about how you can derive your own back propagation logic, right? So why do we need this is that we have already seen that if you have a neural network, you can do a forward pass, you can get the predictions, but the predictions are going to be random because you are just doing some random initialization of weights like we did earlier, right? But what we want is that our network should be able to learn. It should have weights that are meaningful, that can give you good results on maybe classification, regression, or anything, right? So any type of learning you should be able to do, right? So as a deep learning engineer, when you work in industry, you never have to implement back propagation thing because the libraries like TensorFlow, PyTorch, they are automatically going to handle all this thing for you. But since you are learning ML, it's always a good thing to learn something extra. So if I hope I would be able to justify my explanation for this algorithm. But even if you are not able to get the entire thing, it's fine, right? Because what you need is actually is just the forward pass, right? So backward pass can be computed using libraries, mathematical libraries, but we are going to build it from scratch, right? So the whole purpose is to teach you how backpropagation algorithm came and how complex derivatives are being performed, right? So I will start with the explanation part, right? Okay, so yeah, let's see. Okay, so suppose you have a neural network, right? And you have a network like this maybe, and let's say there is only one output layer, there are some input layers, right? Okay, so you have some hidden layers h1, some hidden layers h2, and you have one output layer and you have one input layer, right? So I'm not assuming any fixed network. What I'm assuming is you can have as many hidden layers as you want, right? Okay, so this is how your network look like, and I'm not going to draw each and every edge here, right? The reason is that we are going to understand back propagation and we would be using small diagrams wherever needed, right? So this is your network, and what you get from output is, let's say you're getting some prediction y hat of I, or let's say the final activation value, and let's say this is the last layer. For the last layer I'm going to use the notation let's say capital L, and for the hidden layers I'm going to say I'm talking about the lth layer, so it is going to be a small l, right? So this is about notation. So L is for your last layer and small l is your some hidden layer, right? Some hidden layer, right? So the backpropagation algorithm is needed because at the final layer you know what is your correct output, right? So let's say you wanted to predict a dog. Your algorithm said with I'm 60% sure that it is a dog, but actual output you wanted was 1, right? You wanted it should be 1, right? Or let's say it wanted to predict a cat, so it said the probability of the final output is 0.3. You take a sigmoid and it will become 0. So you have a sigmoid here. Let's say you have a sigmoid activation here, which converts your numbers into your probabilities. So this probability is 0.6, this probability is 0.3. So prediction is going to be 0 and this prediction is going to be 1. So let's say this 1 means a dog, this 0 means a cat, right? So we want to figure out what is the loss, right? So what is the loss, right? So in actual data, let's say the actual output was 1 and 0 only. So the loss we compute is this difference, the predicted values y hat and the actual values y, right? So this is the difference between these two values is treated as loss, right? So let us first start by defining one loss function, right? So the loss function we generally use in classification is your cross entropy, but for simplification, right? So for simplification, I am using the mean squared error loss, right? But the results we are going to derive here do hold for cross entropy as well, right? So I am assuming the loss function, right? Let's say it is L of y hat and y. It is, let's say, half of sum over all examples, the square of actual values minus the predicted values, right? Or let's say y predicted minus y hat of I square, right? So this is I'm assuming for simplification the loss function is a squared error loss, right? So in general this type of loss function is non-convex for a given classification problem, so we generally use cross entropy, right? So this is my loss function, and now I want to see, right? I want to see how a particular weight is, if I change a particular, let's say this is some WLIJ, let's say this is ith neuron, this is jth neuron, and let's say this is W of capital Lij, this is some other I neuron, this is some other J neuron, right? So I want to analyze, if I change a particular weight, how does my loss function change? So if I make a small change in WL of Ij, right, how does my loss change, or how does my error change, or how does my prediction change? Or if I change this WLIJ, how does my prediction is going to change, right? So we can clearly see that there are two types of neurons, right? So one is the neuron which is in the output layer, right? Okay, so the other type of neurons are the hidden neurons. So these are your hidden neurons, right? So the result is going to be different for both of these neurons, right? Because output neurons are directly connected with the loss, right? So if you want to make some changes, if you find there is some delta L should be there, right? So I want to change my loss by delta L, right? Then you can directly figure out what change should I make to make changes to these weights, right? So you need to compute two types of things. One is your delta L with respect to delta W in the last layer Ij, right? And you also need to compute delta L with respect to delta of W in hidden layers Ij, right? So this is what you need to compute, and you also for the similar for the bias term. So delta of bias in the last layer and delta L of delta of bias in a hidden layer, right? So these are the values you need to compute, right? How does loss gets changed if I change one of these parameters? If I change one of the weights or one of the biases, how the loss is going to change, right? So we will treat it as case 1, right, where the weights are associated with output layer, right? And we will call this as case 2, where the weights are in the hidden layer. Okay, so let us start with case 1, right? So let us talk about your case 1, right? Okay, so in case 1, what you are going to have, you are having, let's say, one neuron in the output layer. It is getting some activations from the uh, last layer, right? So some activations are there. So it is getting some activation vector like this: a of L minus 1, 1, a of L minus 1, 2, a of L minus 2, 2, right? So let's say this is okay. So you are getting an activation vector like this, and this neuron again has going to have two components, right? So one component is going to produce your Z, and the second component is going to produce your activation, and this loss is going to accept your actual label Y, and this activation value, which is nothing but Y hat, right? So Y hat is nothing but activation, right? Okay, so let us see, you have only one neuron, right? So your Z, right, and here are some weights WL of 1 comma, let's say this is your jth unit, right? 1 comma j, WL of 2 comma j, and similarly WL of I comma j, right? So you can say the Z of j, this is your Z of j, right? Z of j is going to be summation over all I, W of I j, and I iterates over all the neurons in the last layer L, right? And this is multiplied by a of L minus 1 I plus b of L into j. This is W of L, right? So this is, let's say, the last layer L, right? So we are talking about the output layer, right? Okay, so I want to analyze how this Y is related with, how this Y hat is related with, how does this Y hat change with W of ij, right? So we want to compute this term, right? W delta L of W of ij. This is what we want to compute, right? So we can say the loss depends upon A depends upon Z, and Z depends upon W, right? So Wij is going to affect the value of Zj, and this is going to affect your Aj, and this is going to affect your L of A comma Y, right? So using chain rule, you can say it is going to be delta L with respect to delta of Aj. This is going to be delta of Aj with respect to delta of Zj, and this is going to be delta of Zj with respect to delta of W of Ij. Okay, so is this thing clear, right? Because loss is a function of Aj is a function of Zj, and Zj is a function of W of Ij. So this is nothing but the chain rule, right? Okay, so we can write this equation in this format, right? Now let us talk about what is this term. Okay, let us talk about what is this term first, right? Okay, so let us find out the value of this term, and I am going to denote this term as delta of L of j, right? So this is very important notation here. So remember this notation, so delta of Lj is nothing but, if you just cancel these terms, it is nothing but delta of L with respect to Zj. How the loss is changing according to the. Alright, so let us say that this term that we want to compute is 1, this is 2, and this is 3, right? So let us see what is the value of 1, right? So 1 is your delta L with respect to delta of Aj. So let us first see what is the loss. So loss is given as half of summation over, if you have a layer L, output layer L, and it is producing some output, the final output AL, right? So this output layer has a lot of units I, right? So I'm going to say this is my output of the ith unit, so it is given as AL of I, right? And I have some true output. Let's say the output probabilities are 0.3, 0.5 and 0.2, right? But the true probability is like you will have only one value, right? Say the true probability is 0, 1 and 1, right? Okay, so let's say the true probability is 0, 1 and 0, right? So what you need to do, you need to take a difference between AL and YL, which is the true output, right? So the loss function is squared error loss, which we are assuming as of now. So for over all the output units I, so this is going to be summation of YLI minus ALI and square of this term, right? So the true probability minus the activation produced by the final output layer after doing the softmax, right? Or let's say whatever is the activation produced after applying the sigmoid function, right? So this is going to be, if you take the derivative, so it is going to be half of, if you take the derivative with respect to AJ, right? So this will be only defined when I equals to j, right? For all other terms it is going to become 0. So it is going to be become y of j minus a of j, right? So this is what the derivative is going to be, right? So this derivative comes out to be y of j minus a of j, right? Then let us talk about the second derivative, which is about del of aj with respect to del of zj, right? So del of aj with respect to del of zj. So aj, you know, is a function of is a sigmoid function of zj, or let's say it is some other activation function, right? So this derivative with respect to z is going to be del of aj with respect to del of zj. It is going to be sigma dash of zj. And if it is a sigmoid function, right? So in case of a sigmoid function, the derivative is given by 1 minus sigma of zj into sigma of zj, right? Or you can say sigma of zj into 1 minus sigma of zj, right? So I'm going to write it in this form. It is going to be the derivative of activation function, whatever it is, right? And the third part is we want to compute this value. So delta zj with respect to delta of w of ij, right? So how zj changes with respect to w of ij, right? So again, I'm telling you that some weight is coming in, it is going to change z. Some z is going into activation, it is going to change the activation, and this activation is going to change my loss, right? So I am basically trying to figure out how loss changes with respect to activation, how activation changes with respect to z, and how z changes with respect to w, right? So z, let us talk about the third part, right? So this is for the first part, this is for the second part, and let us talk about the third part, right? Yeah, so let us see what is the third part, right? So you can see your zj, right? So your zj is nothing but a function of w. So we have seen that zj in layer L is given by summation over all I in the layer w of ij, where I is the neural node in the previous layer, into the activation coming in from the previous layer, plus b of lj. This is what we have already seen, right? So if you take this derivative, what you are going to get, you are going to get the activation, right? al minus 1 j. Okay, so this derivative is going to be al minus 1 j, right? So this I'm going to write as a of l minus 1 and a j here, right? If you compute this term, right? If you take the derivative with respect to wij, right? So this coefficient will go off, and for all other terms it is going to be 0, and this is also going to be 0. So you are left with ai l minus 1 j, right? So it is nothing but the activation associated with the previous layer, because you can see, right, if you have a neuron here j, and it is getting some activation al minus 1 from, sorry, this would be your I, right? This would be your ith activation, right? Ith activation from the previous layer, right? So this is I, right? So this is going to be I, right? Because you have a neuron I here in the layer L minus 1, and this is in your final layer L, and it has this weight W of ij. So how does this weight change? It will depend upon this input value activation. That's what we are going to say, right? And for all other weights, right, for all other activation values, this weight is not going to be influenced by other activation values. So it is only influenced by the activation traveling through this edge, right? So it is going to be a of I, right? So this is what it means, right? So now if I combine all these terms, right, so if I now write the formula for delta of L with respect to delta of Wij, it becomes your Yj minus Aj into sigma dash Zj into A of I of L minus 1, right? So this is what it becomes, right? So this is how the weights are going to change, right? So I'm going to write this in a different manner, right? So slightly I'm going to say now this term, right? So this term is going to be my delta of Lj, right? So this term we defined as delta of Lj. So we can say delta of L of W of Ij is going to be delta of L of J, sorry, and this is your J, right? Delta of L of J, right? Capital L is for the last layer, where delta of L is defined by the box, right? Whatever the terms are in this box, into A of L minus 1 into I, right? So this is how you define the changes in the output layer, where delta L is given by, right? Okay, just let me write this term once again. We also need to compute how the loss changes according to the bias, right? So in the output units, in the final layer, you know how the weights are going to get updated. So you know this thing now, delta L with respect to delta of W of Ij. This is now known to you. Now you need to know how the bias is going to get updated, right? So bias, let's say this is some bias B of J, right? So we need to figure out how this bias is going to get updated, right? So delta of loss with respect to bias of J is again going to be written like this, right? So this neuron is going to produce Z, which is going through some activation, and this will be going to the loss function, right? So you need to figure out how the loss changes with respect to activation, how the activation changes with respect to Z, and how Z changes with respect to the bias term, right? So how Z changes with respect to the bias J, right? Okay, now you can see that this term, right? So this term is same as what we have written here. So these two boxes are exactly same, and we have already computed this value. So this value is going to be nothing but delta of Lj, right? So this value is going to be nothing but delta of L of J, and the only thing left is to compute this value, right? So Z you have already seen what is Z, right? So Z is this value, and if you take this derivative with respect to B of J, right? So this value is going to become 0, and this value is going to become 1, right? So this derivative comes out to be 1, right? So this is how your loss is going to change with respect to B of J. right? And so finally what we have, so for output layer, so we got our final formula. We have delta L with respect to delta of W of ij. This is going to be equal to delta of Lj into A of I minus 1 j, right? Sorry, I. A of L minus 1, the activation from the previous layer, this should be capital L, and an I here, right? And we have delta L with respect to delta of bj, so this is going to be nothing but delta L of j, and this activation is now 1. That's it, right? So this is the formula, and where we have already defined delta Lj as what we defined above, right? So delta Lj is defined as Yj minus Aj into sigma of sigma dash of Zj, right? So it is, yeah, it is, I think I made a small mistake here, right? So we also need to take the derivative of Aj, right? So it would be a minus here, right? So when we differentiate this thing, the loss here, right? Yeah, this into minus 1 will also come, right? So this would effectively become Aj minus Yj, and here also in this result, yeah, so it would become Aj minus Yj into, and this is a element wise product with that Zj, sigma dash of Zj, right? So this is the result for the output layer, and I hope you got some insights what is going on, and I will cover the next part in the second part of this video, right? So thank you guys for watching this part, and if you are having some confusion, do go through this video once again, and I hope you will surely get it right.